This is a tune-up of your kinematics skills. My focus will be on definitions, precise use of terminology, and technical details that are good habits. So we have a position versus time graph for an object moving in 1D, and we would like to extract from this graph as much information as is possible. The first general point I'd like to make is about language. If we have here a graph of a function on a grid, but we don't have the equation that describes this function, then we cannot say things like we're going to take the derivative of the graph. You can't take the derivative of a graph, and you can't find the integral of a graph. These are things that you do to an equation. You can take the derivative of an equation if you have one, or find its integral if you have the equation. But here, since we only have the graph, we can't do these things. We have to talk about it this way instead. What we can do with a graph is estimate the slope of lines that we draw on that grid and estimate areas on that grid. So these are what we're allowed to do given the kind of information that we have here. Okay, so let's have a look at the questions. Very first thing we'll note, our position at time 2 seconds. Go over here and see that it's about -3 and meters, units. First of my Kinematics Tuneup tips is to check those axis labels for units. How did I know it was meters and not feet or light years? Check those axis labels. Meters here, seconds there. Okay, so check those labels for the units, and then always include the units on all your numerical values. If your answer doesn't include units, it is wrong. So units everywhere, and on to displacement versus distance traveled. Here's our first definition. The displacement of an object between two moments in time is its final position minus its initial position. So it ended at -1 meter, it started at -4 meters, so our displacement is plus 3 meters. Note that that's greater than 0. We can see that represented here on the graph. This is our displacement, this leg right there. And it tells us that we ended at an x value that was more positive than the x value from which we started. Now, distance traveled, on the other hand, takes into account the fact that we moved 8 meters forward, then turned around right here and moved another 5 meters backwards to get there. The total distance that we traveled was 13 meters. Distance is the sum of the magnitudes of all your displacements along the way. And this is the value that would be recorded on the odometer on your car. The total distance that your car has driven. Your odometer doesn't tell you how far you are at the end away from where you started. It just tells you the total distance that you did travel. Now, instantaneous velocity, defined as the instantaneous rate of change of position. And we can determine this from a position graph because we can find the slope of a tangent line. So going up here to 5.5 seconds, if I want to find the instantaneous velocity at this moment, I can sketch in the line tangent to the graph at that moment, pick a couple of points on that line, draw a little right triangle, and estimate the slope. Okay, so we know it's rise over run, and I'm about to make a mistake as I compute this. So here, the mistake's coming up. All right, I know I want to do rise over run, so this will be 2 boxes here, actually -2 boxes since I'm going down. So -2 boxes on our grid, and then plus 2 boxes over this way on our grid. So the slope of our tangent line, that is our instantaneous rate of change, that is our velocity. So my estimate is that the velocity is -2 boxes over 2 boxes, so -1 meters per second. And I would be wrong. The slope is not -1 meters per second. Why not? Because I didn't check the axis labels for the scale. Check those axes. We see on the x-axis each box is worth 1 meter, but on the time axis each box is worth half a second. The two axes have different scales. So in fact here, this is -2 meters, this leg, but plus 1 second along that leg. So our actual slope is -2 meters over 1 second, -2 meters per second. I can at least get the unit right. That was meters here and seconds there, so we know that's the correct unit. All right, so there we have it, our instantaneous velocity. If we have that, then the instantaneous speed is easy to get because it's just the magnitude of the velocity, or the absolute value of the velocity. So if our velocity was minus 2 meters per second, then our speed is plus 2 meters per second. This would be the value that you would see in your speedometer in your car. Your speedometer, just that positive number that tells you how fast you're going. It doesn't tell you whether you're going north or west or in the positive direction or the negative direction. The velocity tells you that. The velocity includes the direction information with the sign here. Speed just tells you how fast you're going. Next up, average velocity. We computed instantaneous velocity by finding the slope of the tangent line. We can find an average velocity over some time interval by finding the slope of the secant line on the graph. So from 0 to 8 seconds, we can draw a line pointing from the initial position to the final position. Let that line be the hypotenuse of a right triangle, and the slope of that line represents our average velocity over that interval, delta x over delta t. So that's 3 meters over 8 seconds here. And so 3/8 meters per second looks like my answer, but there's a problem. 3/8 is a fraction that's exact. And 3 meters was a measurement, and we know our measurements are never exact. So we cannot report an exact answer in the form of a fraction. We have to acknowledge that our measurements have some imprecision to them always. So here's where we need to mention significant digits. Always report your answers as rounded decimals, never as fractions, to acknowledge that your answer is inexact. And so how much do you round it off? The number of significant digits in your answer should be equal to the least number of significant digits in the input measurements. On the AP exam, they give you a little bit of wiggle room in how many significant digits to use. Usually if you're within 1 or 2 of the correct number of digits, you're okay. So in this case, we have 3 meters, that's 1 significant figure, 8 seconds, that's 1 significant figure. So your answer should have 1 significant digit, but you're allowed some wiggle room there. 2 significant digits would be reasonable. 4 or more would be unreasonable. So 3/8 is exactly 0.375. Let's round that off to 0.38 meters per second. There's our unit, of course. If the unit is missing, it's wrong. Okay, so there's our average velocity. Now average speed. Similar definition, but instead of displacement over time, it's distance traveled over time. So 13 meters over those 8 seconds. So 13 over 8 is 1.625, but we know our value is not exact. It's a measurement, so we have to round it off. 13 meters has 2 significant digits. 8 has 1 significant digit. So our answer should have 1 significant digit. I think 2 would be reasonable. 2 would be okay. So we'll round that off to 1.6 meters per second. Next up, change in velocity, delta V. I'm going to go back to our tips here. A change, represented by that Greek letter delta, is always the final value of the thing minus the initial value of the thing. Final minus initial. So the change in velocity is final velocity minus initial velocity. I just need those 2 pieces of information. So at 5.5 seconds to 7 seconds, let's see, 7 seconds, our final velocity. I know I can find the velocity at that moment by sketching in the tangent line, estimating its slope. I can see that we're at rest, slope of 0 right here, and we know that the velocity at this moment was negative 2 meters per second. So delta V, final velocity 0 minus initial velocity negative 2, comes out to be plus 2 meters per second. Note, that's greater than 0. Our velocity increased. We started at a negative velocity, ended at 0 velocity, so our velocity got more positive over that interval. Hence delta V is greater than 0. Change in speed, we We can also find, if we stick to that strict rule, that the change in the thing is always the final value of the thing minus the initial value of the thing. Final value would just be the magnitude of the final velocity, so 0. Initial value would be the magnitude of the initial velocity, which would be 2. So 0 minus 2 gives us negative 2 meters per second. Note that's less than 0. So our delta V was positive, but our change in speed was negative, indicating that we slowed down. We started at a speed of 2 and ended up at rest, so we got slower, hence delta change in speed is negative. All right, so far we've been able to determine everything that we've been asked for in questions 1 through 9, but on number 10 here, we're asked for the acceleration at a particular time. This is the definition of acceleration, the second time derivative of your position. And once again, we cannot take the derivative of a graph. We can only take the derivative of an equation, and we don't have the equation that describes this function. So it is not easy for us to get the second derivative of the graph here. We don't have the equation. We could estimate the slope of the tangent line, which would give us the instantaneous velocity, but that's not the acceleration. So what can we determine here? Next tip, a few pointers about finding acceleration from a position versus time graph, or finding what we can know about acceleration from the graph. You look at the curvature. If we have upward opening curvature or concave up, that means our second derivative is positive, and we have a smiley face here, smiley face, positive, positive acceleration. If on the other hand we have downward opening curvature, concave down, that's like a frowny face there, negative, sad, negative second derivative, negative acceleration. And if there's a point where we transition from upward opening to downward opening, then we're transitioning from positive acceleration to negative acceleration. There must be a point in between where the acceleration is 0 for a moment. That's that instant right there. So that's what we can know about acceleration from our position graph. Here we see we have downward opening curvature, frowny face, therefore negative acceleration. And that's about all that we can say with much certainty. Acceleration is less than 0 based on this graph. Okay, if you really wanted to get a numerical value rather than just saying it's negative, if you wanted a number, here's what you could do if you had the capability. If you were able to use some software to get a best fit function to this curve, say a best fit parabola to this portion of the graph. And if your software gave you the equation of that best fit parabola, you could then take the derivative of that equation twice to get the acceleration at this moment. So I'll concede that that's one way that you could get a numerical value here. You'd have to first get a best fit function. Lastly, the average acceleration. An average value is always a delta over a delta, change in something over change in something else. So let's see, we've already got our delta V from above that has 1 sig fig. Now our change in time, that's final value of time, 7 seconds, minus initial value, 5.5 seconds. So here's 1 sig fig, 1 sig fig, 2 sig figs. There should be 1 sig fig, therefore, in our answer, but 2 significant digits would be reasonable. So we can round this off to about 1.3, and then our unit, of course, meters per second squared.